In the last lecture, we looked at two solutions to gas in radiative equilibrium. And one was for a gray gas and the other was for non-gray. And the non-gray gas was a very simple model in which gas absorbed in a certain wavelength. So, the gray gas we think about is where the A lambda is a constant, and in a non-gray gas we looked at A lambda had a very simple structure. Okay. So, in the range from lambda 1 to lambda 2 it was constant value, and outside that it was not absorbing. It is a very simple model for non-gray gas, and the results we got for flux was, the flux was non-dimensional flux was equal to 1 by 1/4 3/4 the total outlet thickness, while in the non-gray gas case it was 1 minus T by 1 plus 3/4 kappa 0. So, these two solutions look similar, but they are fundamental difference, and the difference comes in the limit as kappa 0 becomes very large, the optical thick limit, and in the gray gas case Q star tends to 0, here Q star tends to 1 minus D. This is a very important result which is worth remembering, that in a gray gas as you go to thicker limit, the resistance heat transfer is very large and hence heat flux goes to 0. In a non-gray gas, there are always regions in the spectrum where the gas is completely transparent, and hence the radiation just goes through it, whatever the thickness of the gas. So, the 1 minus D is the fraction of the black body radiation lying outside this absorbing region, and so essentially the gas is absorbing only in a narrow region, and so in the transparent region radiation is always transmitted through the gas, whatever the value of A, whatever the absorption coefficient of the gas, as long as non-gray, there are regions called, these are called windows, where the gas is transparent, and hence Q star can never, heat flux can never go to 0. In a gray gas it goes 0. Since all the real world situation that we encounter are non-gray, we must recognize this important difference between gray and non-gray behavior, and this clearly tells us that the gray gas approximation, although very useful to teach certain basic methods and techniques, will not be useful to really deal with the real problem, because the results it will give, especially in the thick limit, are not realistic. So, we must understand the non-gray behavior of these gases. So, now we go back to basic physics and try to understand why do gases behave as non-gray medium with a large variation of the absorption coefficient at different wavelengths. And once we explain this complex behavior, then we will see how to deal with this complex variation of absorption coefficient with wavelength when you deal with the real life problem. In the final analysis, you must remember that as far as the teaching of the subject is concerned, there is not much we can do in the lectures in the class in dealing with complex behavior of real gases. For ultimately today recourse is made to powerful software which incorporates all the complex behavior. And ultimately, most results are obtained by running the software. But the purpose of a course like this is to teach you to understand how radiation behaves in the real world. So, we have to deal with approximation, but at the same time we must recognize the limitation of the approximation. So, we did gray gas knowing fully well it is not a good approximation for real gases. And one example we saw just now, that in the thick limit, a gray gas will say the flux will go to 0, but in a non-gray gas the flux can be quite large, because radiation moves freely through the portion of the spectrum where the gas is not absorbing at all. So, now let us go next to understand the radiative properties of real gases. Now, all of you know that molecules absorb and emit photons, and the absorption of a photon may result in the change in the state of the vibration of the molecule. Molecules vibrate about their center. So, when a photon is absorbed, the molecule may vibrate more rapidly, or it may rotate faster, or it may undergo an electronic transition. So, all the three are mentioned here. Electronic transition, where electrons move from one state to another state, or the absorption of photon may lead to molecule vibrating more vigorously, or it might rotate more vigorously. And you can see that as you move from rotation to electronic transition, the energy required is more and more. This requires very little energy, this requires a lot of energy, and hence only photons in the microwave and far infrared can really be absorbed and create changes in the rotational state, and the photons are a little more energetic are in the infrared region, near or far infrared, then it can induce changes in the vibration of the molecule. And finally, if the photons are in visible ultraviolet, they can really induce an electron to go from the lower state to upper state. The same thing now is stated clearly. Changes in electronic state result in photons being emitted in the visible or ultraviolet region, while change in vibrational state cause photons being emitted in the near to far infrared, while changes in rotation result photons being emitted in the infrared microwave. So, as soon as you see a photon in a certain wavelength range, you must be able to guess which transition in the molecule caused this photon to be emitted. So, just by looking at the wavelength of the photon, you can make a judgment about in which part of the molecule the transition occurred, in the electronic part, or the vibration part, or rotation part. Now, here is a pictorial depiction of the different vibrational states of the molecule 0, 1, 2, 3, 4. So, this may be called the ground state 0, state 1 where the molecule is vibrating more rapidly, and so on. So, since the amount of energy to induce a transient vibration is large compared to the energy required to induce a rotational change. Okay. So, a vibrational state transition will inevitably be accompanied by a small change in rotation, because this is a small value, this is a large value. The analogy can be given to when you are purchasing something, you have an amount in rupees and you have a small change. So, when a photon comes and is absorbed by a molecule, and it has energy slightly more than what is required to take the photon from this state to this state, what it will do is the additional energy will be used to shift the photon not only from v equals 0 to v equal to 1, also from let us say j equals 0 to j equals 1 here. So, a small change in rotation also reduced, so that the complete photon energy is fully utilized. So, a change in vibration is normally also associated with some change in rotational state, and the total change in energy h nu is a combination of change in vibration, change in rotation. Okay. But the rotational change, as you can see, is 1/10 or 1/20th of the vibrational change, and this is shown more pictorially here. This is the ground state, and the molecules can move from the ground state 0 to ground state 1 here, or ground state 2 here, and this is the first excited state, and these are the various, this is the electronic transition, this is vibrational transition, this is rotational transition. Now, let us look at the vibration rotation transition. You can have a change of 1 in vibration accompanied by also a change in rotation. Okay. So, the molecule can move from v equals 0 to v equals 1 and j equals 0 to j equals 1 or 2, and thereby absorbing the full energy of the photon. Now, you can also have a situation where the molecules moves from the ground state of vibration to the first order state, but in the case of rotation, it moves from the upper state to lower state. So, this will mean that the photon that is required to do transition will have slightly less frequency or less energy. So, these are shown in this picture as a vibration rotational spectra of the gas. So, the Q branch is called the pure vibration branch, where delta J is 0, no rotational transition, only pure vibration. Sometimes this does not occur, it is called forbidden transition. And to the right and left are transitions in which there is both vibration and rotation. On this side is the R branch, whose frequency is higher, which means in addition to the basic vibrational transition, the rotational quantum number also increases. So, you require more energy. So, the photons have frequency above nu 0. On the other hand, if the rotational change is negative, that is, the molecule goes from a higher rotational state to low rotation state, then the frequency requires a little less. And so, all these are various transitions possible around a vibrational transition. So, each one of these will be a line of a different frequency, okay. And all of this can occur at the same time, because you may absorb photon with this frequency here to have this transition, and the next photon may have a slightly higher frequency, it will be showing a transition here. So, the spectrum you see of a vibration rotation band of a molecule will show many lines, we will show many examples of that in this lecture. Now, in addition to undergoing a vibration transition of change unity, you can also jump 2 states. They are rare, as you probably know from basic physics, that the most common transition is one in which the vibrational quantum number changes by 1, but occasionally it also at high temperatures can also change by 2 or by 3. These are called overtones. They are rare except at high temperatures, and you can see that the frequencies will go on increasing and the wave number will decrease. So, this is the trans 0 to 1, I am sorry, will increase 0 to 1 transition here, 0 to 2 will be approximately double the wave number, higher frequency, and ground state to 3 will be approximately 3 times this. Our focus will be only on the transition 0 to 1, because that is the most common transition that you observe. So, we summarize the fact that the wave numbers of the rotational transition is in the range of frequency, a wave number from 1 to 500 centimeter minus 1, while vibrational transition are typically in the range 600 to 10,000 centimeter minus 1. And these are much larger than the basic thermal energy of the molecule. Now, how are these changes in energy calculated? In the case of rotational transition, you have to know the moment of inertia of the molecule, and once you know that, based on the mass and the radius of the various atoms in the molecule, you can calculate the energy in terms of the moment of inertia and the quantum number, the rotational quantum number. And so, the change in energy due to a change in rotational quantum number of 1 will be 2b into j plus 1, where b is known as a rotational constant, depends on the moment of inertia of the molecule. Similarly, for vibrational transition, you treat the molecule as a simple harmonic oscillator with 2 masses m1 and m2, and so you can calculate the vibrational frequency as root k by m, the standard simple harmonic motion, and this n plus half comes from quantum mechanical requirements. Here n is the, or j is the vibrational quantum number. Now, one example here is given that of water vapor, carbon dioxide, and they undergo different kinds of vibrating transition. It can be stretching of the molecule or bending of the molecule, and we will give examples of these little later. This is the equation. If molecule with 2 different masses forms a diatomic molecule, then the effective mass will be m1 m2 by m1 plus m2, and so from this you can calculate the vibrating frequency. Here are typical examples of molecules that you encounter in the gases. The main ones, of course, are oxygen and nitrogen. Then we have carbon monoxide, carbon dioxide, and nitrous oxide. Notice that all these are linear molecules. It is aligned in a linear way. These two are symmetric, so they do not have permanent dipole moment. Hence, they cannot interact with the electric field. So, you will not find any strong absorption bands of oxygen or nitrogen, because being linear symmetric molecules, they do not have permanent dipole moment. So, they do not interact with the electric field, and so no transition of radiation, no photon absorption takes place in these two molecules. Carbon monoxide on the other hand is an asymmetric diatomic molecule. So, when it vibrates, there will be change in dipole moment, and hence there is a permanent dipole moment because of the asymmetry, and that will cause absorption and emission of photon. Same thing is true of carbon monoxide. If it vibrates in an asymmetric way, it will have energy transition, but with symmetric, there is no dipole moment there. Nitrous oxide is asymmetric in its very structure. So, any vibration here will create a change in dipole moment and hence cause absorption. Here is water vapor, which is tritium molecule, and it is non-linear, it is not linear, and it is called asymmetric top. Another example is ozone, which is very common in the Earth's atmosphere, and finally methane. So, these are the typical molecules that you encounter in radiation heat transfer in both engineering and atmospheric science. And so, the information that given in the last slide is again reproduced here. Then you see the different modes of carbon dioxide, a very important gas in combustion. You can see that there is symmetric stretching, in which there can be no change in dipole moment, and so it is not radiatively active vibrational mode. But then you have this bending mode, where the molecules in the edges move in a different direction than the molecule in the middle. So, these two bending modes, either it can bend in the plane of this paper or perpendicular to it. And then you have asymmetric stretching, which we will show examples of a little later. For all these modes, you can identify a wavelength. For example, for carbon dioxide, there are absorption bands at 7.5 micron, 15 micron and 4.3 micron. For water vapor, there are absorption bands due to symmetric stretching at 2.7 micron, bending at 6.3 micron, and asymmetric stretching in which molecules move in different direction at 2.66 micron. And methane is a more complicated molecule, so called spherical top, and of course, it has many more number of degrees of freedom. It has 9 fundamental modes of vibration. Some of them are degenerate or similar, so they are degenerate. It has no permanent dipole moment, so no pure rotational spectrum, but there are vibrational modes at 3.3 micron and 7.7 micron. Ozone, a very important molecule in the Earth's atmosphere, has a symmetric stretching mode at 9 micron, a bending mode at 14 micron, and asymmetric stretching mode at 9.6. This is very important band of ozone. Carbon dioxide, we saw it already, so just recapitulation: 7.5 micron, 4.3 micron and 15 micron bands. Water vapor, we saw it already, same 2.7, 6.25 and 2.66. The same information provided in a slightly more pictorial way. So, the symmetric stretching bending as shown here, we will show it in a more animated way a little later. This is nitrous oxide, an important gas in the Earth's atmosphere, and you see it has bands. Now, 7.8, 17, 4.5. You must have noticed that many of these molecules have absorption band very close to 7 and 4 micron, which means when we deal with problems in the real world, we must worry about overlap between these absorbed bands. So, absorbed band nitrous oxide will overlap with carbon dioxide and water vapor, and these must be accounted for in our calculation. Now, here is a model showing the vibration. This is the one vibrational mode, you might symmetric stretching mode. Okay, it is not active because this mode there can be no change in dipole moment. The next one is the asymmetric stretching. You can see that the molecules are not moving the same direction. So, this mode is very important mode of carbon dioxide at 4.3 micron wavelength, very active. And the next is bending, where the molecules go up and down, and you see clearly that this mode is occurring around 15 micron, and this is a very important absorption band of carbon dioxide, because this comes very close to the region where Earth emits maximum radiation. From the Wien's displacement law, you know that a body at temperature around 300 Kelvin will have the maximum radiation emitted around 10 to 15 micron range, and it is this region that carbon dioxide absorbs maximum radiation. And therefore, although carbon dioxide amount in the atmosphere is only now 398 parts per million, its role in Earth's climate is very important, because its absorption band occurs right where the radiation emitted by the Earth's surface is maximum. So, you must remember that the importance of the gas, it partly depends on where the absorption band of the molecule is with reference to the radiation emitted by a surface. And you must have noticed that both stretching and bending have been mentioned, but stretching frequencies are higher than the bending frequencies, because to stretch a molecule it requires much more energy than to bend a molecule. Bending is always easier. You can take a stick and bend it easily, but you try to compress it or stretch it, it is more difficult. So, more energy is required to stretch than to bend, and hence the stretching frequencies are usually much larger. Now, the absorption band of a molecule in the Vibrational-rotation spectrum is shown here. This is the relative absorption. It shows the center band called the Q branch, where there is no rotational transition. Sometimes this does not exist, is not allowed by quantum mechanical rules, but on either side you have the rotational lines which accompany the vibration, the P branch and the R branch, and each one is a line. Okay. Now, very often when instruments are used to measure the absorption coefficient of a gas, these lines are not always visible, because these lines are shown as a single frequency or wavelength or wave number, but on account of various processes which we will discuss soon, these lines get broadened. So, this is called line broadening. That is, what I showed you was a single line at a certain frequency, but this line will actually be a shape like this, and this broadening of this line can occur fundamentally for our purpose two ways, due to collisions. This is called pressure broadening. So, other molecules colliding with the molecule which has absorption band will broaden the range of frequencies in which that molecule absorb. The other is called the Doppler broadening, and this occurs because the molecules are moving at a fairly high speed. So, the Doppler effect will play a role. So, imagine a molecule moving away from you and emits a photon. The frequency of photon that is emitted, that you will see in the laboratory, will be different from the frequency if you are traveling along with the molecule. So, the frequency changes because the molecules are moving at a pretty high speed, and that alters the frequency of that photon as seen by an observer who is not sitting on the molecule, but sitting outside in the laboratory. So, Doppler broadening depends mainly on temperature, because higher the temperature, higher the velocity of the molecules, higher the Doppler effect. Okay. So, the pressure broadening is also called Lorentz broadening. It was discovered by Lorentz. So, Lorentz broadening depends mainly on pressure, while the Doppler broadening primarily depends on temperature. In most of the situations that we encounter both in engineering and in atmospheric sciences, especially near the ground, the Doppler broadening is not that important. More important is the Lorentz broadening, because of the fact that at the surface the pressure is quite high, and so there are lots of collisions which alter the width of the line, and hence you need to take into account the role of collisions due to high pressure, and the Doppler broadening is not that important at the Earth's surface, where most engineering applications are happening. Now, we saw this P branch and R branch, and I said this line ultimately will start broadening because of collisions and temperature. Let us see what it looks like. This is how what it looks like. You can see the, in this case, is a high resolution spectra of carbon dioxide, and it is calculated actually, and you can see that that is the width of the line. The center of the line is right here, but the line actually is broadened. Here is another example, and here you can see that there are so many lines here that you are not able to see the width of each line. It is there, but you are not able to clearly see it because there are so many of these lines. So, this is a challenge we always face in radiation transfer, that in a very small range of wave numbers here, going from 980 to let us say 1040, there are hundreds of lines, and in the center here absorption is high, transmission is low, while at the edge here transmission is high, absorption is low, and your radiative transfer calculation has to take into account the high transmissions in the wings here and low transmission in the center of the band. So, these are difficult calculations you have to do. You can see ideally that you should integrate over all these features to get an accurate estimate of the amount of photons that the gas is absorbing or emitting. Now, here again is a tabulation of the important absorption bands of various common gases like water vapor, carbon dioxide, ozone, methane, nitrous oxide, chlorofluorocarbons, and notice that the regions of the spectra where they absorb and emit photons are very similar. Most of them are in the range of 500 to 1000. And so, this is a point we have to remember, that in any given wavelength range more than one gas can be absorbing irradiation. So, you have to correctly account for overlap of the absorption bands of different gases carefully, because in most situations we encounter the gases which are absorbing are many, and hence their role must be fully recognized. Here are more examples of water vapor bands. You can see the water vapor band starts all the way from 0.72 micron, 0.8 micron, 0.9, all infrared, all these 1.1, 1.38. So, 1, 2, 3, 4, 5, 6, 7 bands are indicated for water vapor here, and then there are these 4 bands of carbon dioxide, more than that, more than 4 are there, 1.4, 1.62, 2.4.3, and in the case of ozone we have 2 important absorption bands. For oxygen there are many bands. Although oxygen does not have a permanent dipole moment, it does have weak absorption bands in the infrared. Then you have nitrous oxide, methane, and carbon monoxide. And here is another tabulation of the various important molecules relevant to engineering and atmospheric science, and this has been put in front of you to highlight the problems we all face. For example, water vapor according to this High-Tran code has 50,000 lines. Okay. Look at ozone, it has 2,75,000 lines. Nitric acid has 1.65 lakhs. So, to me this shows you how difficult it is to deal with radiation by these gases. because they are absorbed over a large number of lines. At the line center, there is strong absorption. So, you can talk about doing this calculation only on a computer. There is no other way to do it, because you have to correctly deal with all the lines, know where the line begins, where the line ends, and what is the peak absorption. So, you can see this is quite a tedious task. So, people have found various simple shortcuts to avoid looking at each line in this complex spectra of the molecules we encounter every day. So, there is also a pure rotational transition, which you will not spend too much time on, because that occurs mainly in the microwave. So, that we will take up little later. Now, here it shows how we go from a line spectra after broadening to a So, our task is to identify the wavelength for each of these lines, and then how the after the line is broadened by collision, how the different lines are overlapping here. So, the two broadening that we discussed, one due to temperature, other due to collisions, they broaden the line and lead to a lot of overlap, and you have to account for all this for you to be able to accurately estimate heat transfer. So, broadly speaking, the optical thickness of the gas is absorption coefficient times the path length, and the absorption coefficient is some intensity of absorption times a function which is a function of frequency, and what function you use depends upon whether in a given situation the collision broadening is dominating or the broadening due to Doppler, that is temperature effects. Here is an example of the pressure broadening of the Lorentz line. So, the shape function for this is some constant times nu minus the center frequency plus some constant a squared. So, this function is a simple belt shaped structure, and this is the most important broadening mechanism of relevance to engineering, because in engineering majority of the time you are dealing with furnaces whose pressure is close to that of atmospheric, or some of them have high pressure, and so all of them will experience this kind of broadening by collisions. Now, in this we saw a constant alpha, and that depends on pressure and temperature. This is called the line half width, because this is a place where when alpha equals this quantity is the center of the line nu equal nu 0, and this is the width of the line half width, and this is important to know because that determines how wide the line is, and this half width depends upon the pressure and temperature of the gas. So, these are all tabulated for different gases. Now, the broadening by collision has two components: collisions by other molecules. Suppose you are dealing with the carbon dioxide molecule and it collides nitrogen oxygen, then the efficiency of collision is a certain amount. But on the other hand, if a CO2 molecule collides with another CO2 molecule, then the energy interaction is more vigorous, because molecules have same mass, and so one has to treat the self broadening due to collision between like molecules, and it is different from foreign broadening, where a given molecule undergoes collision with another molecule. So, that is more common in our examples, because in all our experimentation that we do, nitrogen and oxygen are always there. They may not absorb or emit radiation, but they do play a role. This is the shear function for the Doppler broadening due to temperature of the gas. So, that will be very good. Look at this function. This function is showing exponential decline in the shape function. This is very different from the function that was seen in the case of Doppler broadening, where the broadening, the line is smoothened to a 1 by 1 plus x squared kind of dependence. So, you expect that the Doppler broadening will bring down the line absorption very rapidly to 0, because of the exponential character of this function. And that is shown clearly in this picture. We have the pressure broadening of the Lorentz line and the Doppler broadening Gaussian shape, and you can see that as you go away from the center of the absorption line, the Gaussian the exponential function shows a rapid decline. So, after a certain distance, the Doppler broadening is not important, and the pressure broadening Doppler is not important, and the pressure broadening becomes important, because that goes as 1 by 1 plus x squared. So, there are situations where you must take into account the Doppler broadening in the center part of this curve and the pressure broadening at the edge of the curve, and this is called the white line, VOIGT, which is a hybrid of Doppler and pressure broadening. And here what is shown clearly is the effect of pressure. You can see that the Doppler the pressure broadening, which is influenced by pressure, when the pressure is 1 bar like at the earth's surface, the line is broadened tremendously, while as you go to lower pressure like half a bar or 0.25 bar, then the line is much more sharp. The line is very flat at high pressure and not so flat at low pressure. So, in the earth's atmosphere, the surface pressure is close to 1 bar, while you go to the height about 10 to 20 kilometers, the pressure would have dropped substantially. At about 15 kilometers, the pressure will be 1/10 of the surface. So, you expect that the lines at tropopause will look very different from the lines, absorption lines at the earth's surface. The earth's surface, the adjacent lines will all be absorbed. So, let me illustrate that by an example here. At the earth's surface, where the pressure is of the order of 1 bar, the lines may be all be strongly overlapping because of the so this is what you will expect. The same gas, you reduce the pressure to 0.01 bar, then you will see the same gas will have distinct absorption lines. So, these lines are now non-overlapping, while here they are strongly overlapping. This is very important to know, because if the strongly overlapping lines, then it will remove this complicated structure that you will normally see, and you may be able to fit a very simple function to this. On the other hand, if the lines are non-overlapping, you will have great difficulty in integrating the equation, because between the lines there is no absorption, then suddenly absorption gets a very high value. So, but this does occur with many gases, that there is a strong variation of the absorption coefficient with wavelength, but this is unavoidable condition that we have to deal with all the time. Now, here is one more illustration again of the difference between Doppler broadening by temperature, Lorentz broadening by pressure, and again we are showing here the line width in frequency coordinate as a function of the height above the earth's surface. If you go to very high level, the frequency, the width, half width frequency will be very, very low, but if you come close to atmospheric pressure, that is near the ground, it will be much higher. You can see there is a difference of 10,000 here, width difference. So, this is very important effect of pressure broadening, but Doppler broadening, which is not that much influenced by pressure, but is important at higher altitudes. You can see that beyond a certain height, pressure broadening is not important, only Doppler broadening dominates, that is the upper atmosphere. So, this is the distinction you have to remember between the kind of line which you will get in the upper part of the atmosphere, where Doppler broadening dominates, versus the kind of pressure, kind of line structure you will see near the ground because of the smearing of the lines. Now, to illustrate this further, I am showing you the water vapor band at 820 nanometers. Notice there are a large number of lines here, huge number of them, thousands of them. If you do not want to account for all these details, you can smoothen it and you will get this black curve. But of course, if you calculate your rate transfer based on this black curve, which is highly average, you will make errors, because there are a large number of lines, but between the line there is a gap, and in that gap radiation can escape. So, that will be completely missed out if you use a very smooth function for this. And to make this point clear, let me show a few more pictures of the same spectra. Here the same thing, I want you to look at it. This went from 780 to 860, about 80 nanometers. Now, I take a close up and look at only 16 nanometers, 6 nanometers. You are beginning to see the line, and there is in between a frequency there is no absorption, absorption 0, transfer is 1. So, you have to tackle this high absorption at the central line along with the adjacent wavelength having no absorption. So, this is the challenge of calculation in radiation heat transfer, is that the absorption of the gas varies strongly with wavelength, and small change in wavelength or wave number or frequency cause a large change in the radiative flux. Now, the same graph, this is now only 8 nanometers. Now, we go further up, this is now only 0.4 nanometers, same spectra. Here you can see you are able to resolve everything. You see here there are 3 major lines which absorb strongly, and in between region there is hardly any absorption. And so, you have to get this close to the spectra, that is variation with 0.1 to 0.2 nanometer, before you can really resolve the shape of these lines. Now, this point is further illustrated in this graph, where the transfer of carbon dioxide through a 1 meter depth of the gas is shown for surface pressure, where you see a large number of lines with a center region there. Now, if you want to know what happens when the same gas is looked at, we take this portion between 665 and 670 and expand it. You can see that there are some, right in this slope region, there are beginnings of the line structure visible at 1 bar, but take the same gas and find the spectra at 100 millibar, that is about height of 10 kilometers, 12 kilometers. You can see that these lines, which are hardly visible here, they are actually distinct lines. Here they got overlap, at the earth surface they got overlap, but once we bring the molecule to a higher elevation, all this will come out. So, this has to be remembered, that the actual shape of the line depends upon the absorption spectra of the molecule. And one more illustration here of the oxygen absorption in the microwave. You can see that at 100 millibar pressure, very low pressure, each line is distinctly visible, but as soon as you go to surface pressure, all this is smeared out and you are only getting a smooth curve. Any calculation using this will be very crude, any calculation using this will be very tedious, but at the end of the day it will give you very valuable data on CO2 absorption and emission. Now, this further illustrated from satellite data. I have shown 3 different satellites, flux as calculated based on the concept of brightness temperature. So, brightness temperature is that temperature at which the black body emits the same intensity as the actual emission you saw at a given angle at a given wavelength. Now, this carbon dioxide band is shown by 3 different satellites. The older satellite is GOES, which had a very poor wavelength resolution. So, you get a very smooth curve. On the other hand, you look at other satellites like IRIS or high resolution, high infrared. You can see that the high resolution spectra here shows the line structure, which is just about visible here, is almost gone in the case of the older satellite. As you go from older to newer satellite, the resolution is improving continuously. So, newer satellite giving you much more structure, which has some value for interpretation. Now, because of all the absorption, all of you know that the radiation that is coming from the sun behaves close to that of black body, that is the orange line. By the time the radiation goes through the atmosphere, is absorbed by various constituents, at the earth's surface the radiation is lower and there are clear cut absorption bands of carbon dioxide and water vapor, which you see here, which has removed the black body radiation that was being emitted by the sun. And so, blue is the spectra observed at the earth's surface, while orange is the spectra at the top of the atmosphere, and wherever these two differ is due to absorption by molecules. Now, here is another spectra as obtained from satellite over the Sahara region, and you see very clearly the strong absorption by carbon dioxide in the 14 to 16 micron band, and carbon dioxide absorbs radiation from the earth very efficiently and then re-emits it at a temperature corresponding to the cloud tops, and hence the temperature that you notice when you measure it will be very low here. And this is ozone. The ozone CO2 are they are already sitting there in these locations, and they will absorb, and only that the earth's black body spectrum maximized somewhere around this region, and that is why carbon dioxide is playing. Without carbon dioxide, the earth's emission would have been like this, and with carbon dioxide now there is a big dip here, which is the role of carbon dioxide. This is the role of ozone. Water vapor plays an important role here, much larger wave number, which we will see later. Here are more examples of spectra from Antarctic and Sahara, and we are showing this to show the huge difference between Sahara and Antarctic. In the case of Antarctic, there is an inversion near the surface which leads to such a peculiar spectra, and it is very different from the Antarctic, where water vapor absorption dominates in Sahara. And here are more examples of spectra of water vapor, and the water vapor spectra, you can see the difference between Nauru in Western Pacific and Barrow in Alaska. This is a cold place, this is a warm place. So, in a warm place, the atmosphere emits radiation more vigorously, and in both cases the presence of gas has reduced the emission spectra substantially. Now, here is an example of transmission from surface to 11 kilometers and surface to space. If we take to surface to space, then you are taking into account all gases that are there in the Earth's atmosphere, all the way from the ground to maybe 100 kilometers. But if you compare the spectra of the atmosphere layer from surface to 0 kilometers, we should also ask to look at the corresponding spectra from space to space will be anywhere around 15 kilometers or so, and you see that this spectra differs substantially between what you do for the total integrated spectra up to the top of the atmosphere and the one in which you look at only at the top of the tropopause, and you can see the widths have changed because this example of this region with the high transmitted became a highly absorbing region, and so this is the peculiar to radiation transfer. Now, let us also get some definitions going. In the next lecture, we will define the absorption coefficient and the amount of absorber and go along to depict these values in real situations. Thank you.